Hi, welcome to Linear Algebra. Today we are going to have a general discussion about the course itself, and then we are going to talk about the nitty-gritty details in the next lecture. So you are here probably because you are in STEM degree, science, technology, engineering, or mathematics. Majority of you are coming from engineering, and perhaps a few are from mathematics, physics, chemistry, or other sciences. Most of you are asked to take 6 courses in applied mathematics. These are Calculus 1, Calculus 2, Calculus 3, Linear Algebra, Differential Equations, and Statistics. Of these 6, Linear Algebra is kind of the odd man out. It has a reputation for it too, and today I want to dispel some of the negative connotations that might be associated with this class in your mind. Linear algebra can be approached from a practical point of view or from a pure point of view. We are going to start the course from a practical view approach, and hopefully you are going to take a next class in pure view of linear algebra that's going to be a foundation for advanced mathematics. So let's go ahead and see how does linear algebra relate to practical issues. So as an engineer, you are going to be building a variety of devices and structures, and one thing that you are going to be worried about is vibration. Most structures do vibrate, and sometimes it's a welcome sign and sometimes it's an unwelcome sign. I would like to propose that another name for this class is theory of vibrations. At the first sight, it looks very far removed from the content of the course, but as we are going to progress through the topics, you are going to see that there is a direct connection. So, where are the places where you see vibrations? Well, you see vibration pretty much everywhere. Large structures do vibrate. That includes skyscrapers. Most electromagnetic devices are built on special kind of a vibration. So one way or another you do deal with them. Let's take a look at some notorious examples of vibrations in history. This is the case of Tacoma Narrows Bridge. Let's take a look at that. A bridge that was constructed around 1940, and one day the wind start to blow and the bridge start to oscillate in a very strange manner, and as a few hours passed, the bridge collapsed under that vibration. Of course, you don't want to be on such a bridge, and also you don't want to have your name associated as an engineer with such a bridge. So obviously we need to know about vibrations, how structures vibrate, to be able to predict such a thing and to prevent it. Well, you think the people involved learned their lesson, but amazingly enough, 60 years later it happened again. So let's take a look at this one. This is the
bridge opened on the 10th of June 2000, attracting thousands of people and the media. But as the people poured over the bridge, it was clear something was wrong. The bridge was wobbling from side to side.
I got a phone call midday saying we have a problem, and my first reaction was same as everybody else's. Well, all bridges move a little bit. There's an exaggeration going on, but Roger said no, this is real. And so I came down early afternoon, and you saw it, and you think this isn't real. This can't be happening.
It was very disappointing. We were witnessing the bridge performing in a way that we hadn't anticipated. We'd done lots of work to try and understand its behaviour. We felt that we understood it very well, and here it is doing something completely unexpected.
The engineers had tested every element of the bridge, from the cables and bolts to how the bridge would behave. Regulations and codes of practice give engineers basic design guidelines. These codes are based on years of experience and look at how different vibrations can affect a bridge. In 1941, the effect of wind-induced vibrations was fully understood after the Tacoma Narrows Bridge in America collapsed under a strong, persistent wind. But it's not just the elements. Soldiers marching can create sufficient vertical vibration to bring a bridge down. Before crossing, they're always ordered to break step. Signs on some bridges still bear witness to this danger. As engineering advances, the bridge building codes are continually updated. Arup researched beyond the requirements of the codes, studying pedestrian vibrations in detail.
With regard to pedestrians, we did a lot of work on vertical vibration. That is, as a pedestrian walks over the bridge or a group of pedestrians, what kind of force, repetitive force, do they put into the bridge?
Arup's calculations followed the codes in assuming that people walked randomly and the major force they generated was vertical. But on the Millennium Bridge, something unexpected happened. People changed the way they walked in reaction to the movement of the bridge. To balance themselves, pedestrians spread their feet apart, creating a significant lateral, not vertical force. More importantly, the people's reaction was almost identical. Everyone stepped the same way at the same time, creating a synchronized rather than random force. The frequency of this force matched the natural frequency of the bridge.
The motion of the crowd was synchronized with the motion of the bridge, and that's actually proved to be a very important observation. We also observed a quite bizarre behavior, that we could control the level of vibration by limiting the number of people. But it was far from a linear relationship. We noticed that it was almost an on and off situation, that either, the center span particularly, either it was vibrating or it was fine.
The vibration developed when a large number of people picked up the slight movement all lightweight bridges exhibit and locked into it.
Lock-in is the term that we've used to describe the fact that people, as they walk over this moving surface, sense that movement and adjust their gait to take account of it, to stay up, to keep their balance.
Lock-in seemed to be a problem no one had come across before. But Arup then identified two bridges that appeared to have a similar problem, one in Japan and one in France. However, reports of the problems on the Solferino Bridge in Paris were confused, and they did not identify the cause. In Japan, engineers did publish their understanding of the phenomenon, but in a journal of seismic engineering, unlikely to be read by bridge engineers.
The body of knowledge hadn't disseminated beyond those people, and Arabs didn't know about it, I didn't know about it, and specialist checking engineers, who are the most likely people to have known about it, didn't know about it.
As news of the bridge spread, Arup received reports of other bridges of all shapes and sizes that had wobbled. This meant that any bridge with a low natural frequency carrying large numbers of people could begin to sway. Clearly, the phenomenon was not caused by the Millennium Bridge's innovative design.
Okay, so we took a look at London Millennium Bridge. We saw some examples of vibrations, and we said we want our course to be called Theory of Vibrations. Let's go ahead, take a look at something that you can duplicate in your engineering laboratory and see the situation for yourself and be amazed by some of the basic connections. So next video we are going to take a look at three structures that respond to a vibrating foundation. It's going to show a phenomena that actually later on I can ask you to do in a project if you wish to have a project for a class. Let's see what this one is about. So we have three structures. These are just 4 bars with some weight on top of it. They're sitting on a vibrating table, and we are going to increase the frequency of vibration, see what happens to these 3 objects. Doesn't look very exciting at the beginning, but just wait. So the frequency has increased. You notice that at a frequency of 4 Hertz, the tallest structure here starts to vibrate rather widely, while the other 2 behave as if nothing special is happening at all. So we are going to increase the frequency some more and see what happens. Notice now at a frequency of 6.35, the middle one in our setup starts having the wildest oscillation, while the other 2 now behaving as if nothing special is going on. So you can probably predict what's going to happen as we increase the frequency. Noticed at the frequency of 11, the shortest one starts to have wild oscillations, while the other two just stay put without essentially reacting. So this is an example of resonance, and that project that I'm suggesting also tries to analyze this mathematically. For the last video that I'm going to show you today, we are going to take a look at tuned mass damper, or TMD. Those of you headed to civil or structural engineering probably going to deal with this thing directly. And let's take a look at this one as well as our last lengthy video.
In many of the world's tallest skyscrapers, there's a secret device protecting not only the building, but also the people inside from strong motion due to wind and earthquakes. Did you know you can tune a skyscraper just like a guitar?
Hey, I'm Grady. Today on Practical Engineering, we're comparing theory to the real world for tuned mass dampers.
What do a marble in a bowl, a guitar string, and a skyscraper have in common? Well, you're on the wrong YouTube channel if you think this is a joke. I'm talking about physics. All three are examples of oscillators. An oscillator is just a system that when you displace it from its equilibrium position, it experiences a restoring force. I move this marble from the center of the bowl, it experiences a force, gravity, pulling it back toward the equilibrium position. I pull on the guitar string, the tension in the string increases, trying to pull it back to the center. When the displacing force is released, the system oscillates about the equilibrium point. What about the skyscraper? Maybe this sweet montage will help answer that. Sometimes to the detriment of the hedge fund managers and penthouse denizens on the top floors, a skyscraper can act as an oscillator just like the marble and the guitar string. Wind can induce oscillation in a building just like a tie-down strap on a vehicle. A strong earthquake can also excite the building's resonant frequency just like plucking a guitar string. In most cases, the movement's not enough to threaten the safety of the building itself, but that amount of movement can be profoundly uncomfortable to its occupants. Most of us hold an intrinsic belief that buildings should not move. We don't even think about it. For our entire lives, Wednesdays come after Thursday, the sun has risen in the east, and our domiciles and dwellings have remained static beneath our feet. So you can forgive your subconscious for feeling some amount of terror when such a fundamental belief is shaken, especially when the shaking is literal. It may not be enough to harm the building's structure, but it's certainly enough to cause a 1%er on the top floor to lose his caviar. And buildings aren't good for much if people don't want to be inside them. So engineers have come up with some novel solutions for minimizing this unwelcome vacillation. And I want to talk about one of those today, the tuned mass damper, or TMD. A TMD reduces the amplitude of vibration by absorbing kinetic energy from the system, in this case the swaying motion of a tall building. For a long time, TMDs were relegated to areas with the rest of the building's mechanical equipment, hidden from public view. That changed in 2004 when the Taipei 101 tower finished construction in Taiwan. Rather than hide the world's largest spherical tuned mass damper, the building's designers chose to open it to the public. Taipei 101's TMD has become a draw for tourists and even has its own mascot, the Damper Baby, which looks like it came straight off the island of misfit mascots. Anyway, the publicity associated with the Taipei 101 has sort of unveiled this really cool bit of engineering that is the tuned mass damper, and you can find tons of videos of it in action online. So how does it work? I've constructed this model of a pendulum-style tuned mass damper in a skyscraper. I can pull the cart back and give the building a bump, which excites its resonant frequency just like an earthquake or a strong wind event. The benefit here is that I can do it in a somewhat repeatable fashion so we can evaluate the effectiveness of the damper. For the TMD, the damping comes from the tension of the screw, which is acting as the hinge. I can tighten the screw to increase the damping. The tuning comes from moving this mass up or down on the pendulum shaft. This changes the frequency of the pendulum just like a metronome, which can be tuned to the resonant frequency of the building. I have an accelerometer on top of the building so we can measure its movements, and this is hooked to an Arduino which is sending the data to my laptop. There's more in the description below if you're curious about the data collection. If I lock the pendulum and set the building swaying, we can get a sense of how it would perform with only the building's own natural damping. Plotting the acceleration response, we can see that the model experienced a maximum amplitude of about 4 meters per square second, or half a g, with a period of 0.6 seconds. Frequency is the inverse of period, so we can get the building's fundamental frequency, 1.7 Hertz. We can also see that the building has some natural damping just due to the internal friction in its movement. Otherwise, it would just sway indefinitely. We can estimate the model's natural damping ratio using the logarithmic decrement. I get a damping ratio of 0.01. The damping ratio, denoted by one of the tougher Greek letters to draw, zeta, is a measure of how quickly the amplitude decays in an oscillating system. Systems with a damping ratio greater than 1 are said to be overdamped because the system returns to equilibrium without oscillating. Systems with a damping ratio less than 1 are said to be underdamped since they experience some oscillation. If the damping ratio is exactly 1, the system is critically damped and returns to equilibrium as quickly as possible. And if the system is undamped, the oscillation continues indefinitely. There are lesser known damping situations, but we won't get into them in this video. Now that we know an approximate natural frequency of the building, we can introduce the pendulum damper. You may remember from your physics classes that a pendulum's frequency depends on its length. For a frequency of around 1.7 Hertz, my pendulum needs to be approximately 3.5 inches long. Now let's try the exact same experiment with the pendulum able to swing freely. The kinetic energy of the building does get transferred to the pendulum at first, but because there's no damping, the pendulum transfers the energy right back into the building. So, instead of reducing the amplitude, instead the pendulum just continuously swaps the kinetic energy with the building like a hot potato. You can only imagine that this erratic behavior would be even more alarming to our topmost tenants than the steady but slowly decaying motion of the previous example. Now, let's tighten the screw to add some damping to the pendulum and see what happens. Even without looking at the data, you can see a remarkable difference in performance. Looking at the plot of acceleration response, we can see that the peak acceleration was about 3.5 meters per square second, so a reduction of only about 12%. But the big difference is how quickly the motion decays. At the beginning, when the pendulum is swinging, I calculated a damping ratio of over 0.6. That's about 6 times more damping than without the TMD. Once the pendulum stops swinging, the rest of the swaying follows the approximate natural damping ratio of the building itself, as expected. But the majority of the kinetic energy has already been dissipated by the damper, so the amplitude is much lower. Here's a slow speed side by side so you can really compare the two. As silly as this little experiment looks, it's actually not that far off from what engineers do in the real world, usually without the googly eyes. The design phase for just about every major building includes some physical scale model tests. Of course, a tuned mass damper doesn't completely eliminate movement, but we saw that it can certainly make a difference. In engineering, you have inexpensive, you have effective, and you have innovative, and usually you get to pick one, sometimes two. For solving the problem of oscillation in tall buildings though, the tuned mass damper is truly all three, a great example of elegance in engineering. I hope you liked the first practical engineering video, and if you did, I would really appreciate it if you would push that like button and subscribe to the channel. That helps motivate me to keep making cool stuff. If you want more details, have a question or suggestion for a topic, and especially if you live or work at the top of a skyscraper, I would really love to hear from you in the comments. You can also visit my website, practical.engineering, to learn more. Thank you for watching, and let me know what you think.
Okay, that was an exciting video. The work that we are going to have in this semester is not going to go that deep into civil structures and the designs of that type, but it's going to be close. He talked about energy going back and forth between the damper and the building itself, and the next animation that I'm going to show you is going to actually have a connection to that. And this is the demo that is being explained in the projects that we usually do with respect to this class. So the first one is an example of a triple spring. See if it comes up. Yes. So we have 3 springs attached to 2 masses, and then we are going to wiggle one of them and the whole thing starts to move. Looks like a very simple structure. In some sense it is. But to understand it, you actually do need 2 courses. Differential equation class and the linear algebra class. That is, if you want to truly understand the mathematics behind this movement. Let's go ahead and take a look at that and see if you can detect some peculiar behavior here. Let's go ahead and perhaps show it to you a couple of times so that you can look at it and see. Of course, if you want to play with it, you can go back to my website and just look at all of these things individually at your leisure. But here, let's go ahead and play this video. So we have moved the left ball and it starts to move, and that influences the right one. And do you notice something peculiar happening? Let me show it to you again. If you missed it the first time, then probably now you are going to notice it, that first the left one had the maximum amplitude, then it comes to pause while the right one starts to amplitude to oscillate at high amplitude, and then it goes back and forth. The energy somehow goes back between the 2 balls. Understanding that behavior, predicting it mathematically, requires this class. It actually, the entire class all the way to the very end, when we talk about eigenvalues and eigenvectors, come into play for explaining that kind of a behavior. So any kind of a system that you have made out of several components that influence each other, if you want to study the behavior of such structures, you do need linear algebra. And of course, you always need differential equations anyway. So here's a similar setup. You can actually do this thing at home. All you need is just some string here, tough string, and then 2 thinner perhaps strings attached to 2 masses. And even without this spring between the 2 of them, you are going to be able to notice this kind of a behavior. So let's just go ahead and start this thing. This animation is very similar to the previous video. You notice that we are moving one of these pendulums, say pendulum number 1, and that caused the number 2 to move, and then number 2 is going to cause number 1 to move, and the energy goes back and forth between the 2 of them. Of course, the details depend on a variety of things, like what's the property of this spring, how about that string here, the structure up here, and so on. So again, if you have several items, several objects whose movements influence each other, in that case you have a system. The analysis of the system requires linear algebra. In linear algebra, we are going to study systems of equation. That's the same word here. That system reflects the presence of several entities whose movements influence each other. To analyze that, we need linear algebra. And then, of course, to analyze motion, we need differential equation. Together, we have theory of vibrations. So, that is a justification for this class. Of course, much of the time you're just dealing with the x, y, z's and learning mathematical operations and so on. But if you follow the discussion up to the end, then you see the mathematical explanation of vibration. Okay, so in the next lecture we are going to start talking about vectors, and then we are going to have planes and lines and so on, geometrical ideas that match the concept of a linear in the title of this course. All flat objects are going to be studied first. Then we are going to look at intersection of these things, intersection of planes, and we are going to see that that by itself gives rise to the system of equations. So over there we have a system of equations coming out of geometrical considerations, like if you have two planes intersecting with each other, how do you describe that event? Well, you need systems of equations. And then we are going to talk about properties of these systems, special types of systems, how to write the solutions of systems, and so on. And then we are going to move on later on to how linear objects get mapped by special creatures called matrices. We are going to talk about that. And then matrices toward the end of the class, we are going to study certain properties of matrices called eigenvalues and eigenvectors. These things associate with the frequency of vibration that we are seeing. Eigenvalues are connected to the frequencies. Eigenvectors connected with the modes of motion that we see in these vibration problems we saw before. Okay, so hopefully I motivated you to look at this topic carefully. Again, we are looking at it from an applied point of view, and then there is an advanced linear algebra class that looks at it from a pure mathematics point of view, more of a philosophical nature than what we are going to have here. Until the next meeting, good luck and God bless.